Okay, so last time we covered linear optimization problems and linear optimization models in Excel, working specifically with decision variables of 3 or more that can't be done as easily by hand, and then using Analytic Solver Platform, the software plugin we have for Excel, to sort of specify the linear optimization problem in 3 different segments: the decision variables, the objective function, and whether we maximize or minimize, or how we, what kind of optimum we're looking for, and then constraints. Okay, so I thought it would be helpful just as a matter of mostly review. We can talk for a few minutes anyway about assignment 4 and how that's going. I've received a couple emails today I hadn't had the chance to respond to yet, just some general questions about getting started and how to do some of the problems. And so I thought maybe it'd just be useful to cover that in class tonight. So I have assignment 4 here on the screen. The first problem, so both of these are word problems, descriptions of a situation in which linear optimization is going to play a role in determining what kind of solution or what kind of decisions would be optimal to make. Okay, so in this case, a company's producing bookcases. They have 3 different types: standard, wide, and narrow, that they sell. Now, those bookcases require work from effectively 3 different departments, or 3 different things have to be done to them. One is trimming, one is shaping, and the other is assembly. And depending on the bookcase type, they require different amounts of work, okay, different times taken to assemble them or times to make those bookcases. And then naturally we're going to have capacities on how many hours we can spend in those 3 different phases, or 3 different departments, or 3 different types of work we have to do. And then each bookcase sells for a particular profit. And so just given that information alone, the first 3 questions we would always ask are: what are the decision variables, what is the objective, and what are the constraints? Okay, the decision variables in this case, hopefully everybody was able to sort of figure that part out. The decision variables are how many bookcases of each of the 3 types do we want to make. Okay, so let's just say, for example, I'll use the board behind me. Since we have standard, narrow, and wide, we'll just use variables S, N, and W as the decision variables. So we need to find values to assign to those 3 variables, okay, to decide how many standard bookcases to make, how many narrow, and how many wide bookcases to make. Okay. So the next question would be, what's the objective function? And I believe it says in the problem description, but as with most problems, you're either going to minimize costs or maximize profit. In this case, we're given profit numbers, and the question is, how do you maximize profit? By building the right number of the right kinds of bookcases. So the objective function, okay, is going to be a linear function of these 3 variables, the decision variables, okay, and it's something we're going to maximize. Okay, so what we want to maximize is profit. Well, for every standard bookcase we make, we can make $8. So $8 times S plus $6 times N, number of narrow bookcases, plus $10 times W, okay, is the objective function. Okay, so I mean, whether you want to say that equals, Z or something, you want to assign a variable to it, you wouldn't have to, right? The idea is whatever value comes out of this equation, we want to maximize that value. Okay? So we don't know what value we want. We don't even know what values necessarily are possible yet. All we know is, right, that's how you would compute the value that we're wanting to find, values of these variables to maximize this, right? But we have constraints. So the third component of every optimization problem are going to be the constraints. Okay? And in this case, we have 3 different things that have to be done to make each of the 3 different types of bookcases. and we have capacities on how much time or resources we have available to do those three activities. Okay, so the first activity was called trimming, and trimming requires 0.2, I guess they're hours, 0.2 hours for every standard bookcase, so 0.2 times the S, number of standard bookcases we make, plus 0.4 times N, plus 0.6 times Y, right? That's how many hours we're going to have to spend in trimming activities or trimming work for the given number of S, N, and W bookcases we're going to be making. And the key is, or the constraint is, that the machine required to do the trimming only has 150 hours available. So whatever values of S, N, and W get picked, the value of this side of this inequality has to be less than or equal to 150. That's the total amount of time we have available. And similarly for the machine or operation known as shaping, different coefficients, but it is similarly limited to 150 hours. Okay? So we have our decision variables, we have our objective function, the first two of our constraints. The final constraint was in assembly, which the problem states requires the same amount of hours, 0.4, for all three types of bookcases. For W, and that is limited to, let's see, 600 hours. Okay. So, decision variables. So in Excel, we create and label cells, I guess, for values to put in to represent S, N, and W. We compute the objective function as 8 times whatever value is chosen for S, 6 times N, 10 times W, added up together. And then we'd compute 0.2 times S plus 0.4 times N plus 0.6 times W, and we would tell Analytic Solver Platform that the value of that, whatever that sums to, is constrained to be no greater than 150, and so forth. Okay? So 3 constraints, 3 decision variables, okay, in the objective function. Any questions about generally how to set up that problem? Okay. All right. Good then. So you would just have to put in Excel, right? Effectively this information, okay? Using Excel formulas to compute objective function and constraints, and then Analytic Solver Platform to tell it where the 3 decision variable values are, where the computed objective function value that you want maximized is, and where the computed value and constraints are, limiting numbers for the constraints are, for the 3 constraints. Looking through the questions in the homework, so, well, not a question, but part A, construct the linear optimization model in Excel. Okay, we talked about how to do that. Question B, what are the optimal production quantities for the company? So maybe a little bit funny worded, but I'm just asking, so how many standard, how many narrow, how many wide bookcases are made in the optimal case? When we've maximized our profit, what are the values found or chosen for S, N, and W, as we said? Part C, what is the pattern in the optimal allocation? So as we did last week, when I say the pattern of the problem or the pattern of the optimal solution, I just mean in words, describe to me what happened, what trade-offs were chosen. Did we choose to make more standard bookcases, or did we choose to make more wide bookcases as they're more profitable? Did we choose to make no bookcases of one of the 3 types? Right, those sorts of things. Okay, so just in your own words, describe kind of what you feel like aptly describes the pattern of that optimal decision variable values. Okay, and then part D, using optimization sensitivity, how much profit would wide bookcases need to make per unit before the optimal solution pattern from parts A and B would change. Okay, so right now we say we make $10 for every wide bookcase. Okay, sort of under the assumption that we're not only making wide bookcases. Okay, how high would that profit value, that parameter to the model go? That 10. Should it be 11? Should it be 12? Should it be 13? How far do you have to go before the pattern to the optimal solution changes? That is, it decides to make more wide bookcases than before, and presumably less standard or narrow bookcases. Okay, so we talked about and saw examples of using optimization sensitivity last week, where you define the optimization parameter. Okay, in this case, it'd probably be a parameter you wanted to start with a lower bound of 10, maybe an upper bound of 20 or 30, presumably somewhere in there. It would optimize for every step in between those two bounds and show you what, or it could show you what the optimal decision variables were and the optimal profit. Now, obviously, the profit might change for every step, right? Presumably, if you're making any wide bookcases, well, as the profit of wide bookcases goes up, total profit would go up. That doesn't necessarily indicate it made a different decision. That is, it may still be making the same number of each type of bookcase. So the question in Part D is, at what point for profit of wide bookcases does the optimal decision variable values change? So when does it make more wide and less standard and or narrow bookcases? Any questions about what's being asked in that question, or sort of how to do it? Okay. All right, and then it says, how does the optimal solution change? So just describe that. Which bookcase type did it make less of so it could make more wide? And how many? How much? Okay. All right, so let's talk a little bit about problem number 2. So problem number 2, an Apple products company makes apple juice and applesauce. There's a cost for each unit of those that is made. And there is a blending or a blended constraint that says you can't choose to make less than 20% of total product or more than 60% of total product in applesauce. That is, the company kind of wants to blend or kind of wants to balance making applesauce and apple juice. It doesn't want to make too much apple juice, not enough applesauce, or vice versa, for whatever reason, right? Just trying to hedge against problems in the market, maybe, for selling those kinds of products. So it wants to have both products being made in something between 20 to 60%, roughly, ratios. Okay, so getting on to more of the parameters of the model, it's estimated that the demand for applesauce is 5,000 jars plus, so it says maximum of 5,000, but plus 3 more jars for every $1 spent in advertising. So if we didn't advertise our applesauce at all, we suspect that 5,000 people would buy it. Okay, if we spent $100 in advertising, okay, commercials on TV or radio or whatever, we suspect those same 5,000 would buy applesauce, but an additional 300 people would hear about our product and consider and come and buy it. Okay, so the more you spend on advertising, the more you can sell. Right? Kind of intuitive. Similarly for juice, the base demand, I guess I would say, is 4,000 bottles plus 5 bottles for every $1 spent in advertising. The company has $16,000 to spend on both the cost of producing the products and advertising. Okay, so if you make, let's say, 1,000 jars of applesauce, it costs 80 cents a piece. So if you made 1,000 of them, it cost $800. Okay. Plus, if you wanted to advertise it, right, you'd have to pay for that as well. Okay, that cost of producing the products and advertising for them is constrained to be $16,000 or less. Okay, and then finally, applesauce sells for $1.75. Apple juice sells for $1.75, and the company wants to know how much advertising dollars to spend in order to maximize profit. Okay. So the decision variable is the number of dollars to spend advertising, apple juice versus applesauce, and we're going to maximize as our objective profit made. Okay, so I kind of spell that out. Now I think I also say somewhere here, that so we choose to spend dollars in advertising. That adjusts the demand, how many you can sell. I think we're going to assume in this model that we sell as many as we can. So if we can produce 6,000 jars of applesauce and we can spend enough in advertising to create a demand of 6,000 jars, that many will sell. Okay, so we're kind of assuming that as many as we can make legitimately, between spending advertising dollars and spending money to produce the product, we'll sell it all. Okay, so 100% sales rate, I guess. All right, so construct the model and then so forth. So let's do a little bit of this one anyway by hand. So decision variables are the advertising dollars to spend on applesauce and apple juice. Okay. The objective function, okay, is going to be based on how many we sell, right? So before we can compute the objective function, right, we have our decision variables of how many dollars to spend in advertising, but that doesn't directly tell us how many we sell or how many we can make and sell. So we need to compute, so I'm going to do that in a separate row here. Oops. Fix that. I'm just going to call this calculations. Okay. So we know that for applesauce, the demand, or how many we can sell, is going to be 5,000 plus, I believe it was 3 times the number of advertising dollars made. Okay. So I'm just going to compute that in this cell and say this is the demand or the amount of product sold. Okay. So for now, applesauce, we can sell 5,000 jars because we so far have chosen to spend $0 advertising. Okay, let's make that look like a currency. There we go. And similarly for apple juice, I believe it was 4,000 base demand plus 5 times every dollar spent advertising. Okay, so that tells us how many units of the product we can sell based on how much advertising we did. Now for our objective function, we can compute, let's see, I believe it was $1.75 profit for each. So we can compute using some product the number of product we sell, right, times the amount we make per unit profit for a total profit. Okay. Those will all be currencies. All right. So now we can come to constraints. So we have our decision variables, which is just 2 decision variables, the amount of advertising dollars to spend. We had to do some sort of intermediate or preliminary calculation based on the decision variables to know how many units we can sell. That's a linear function, obviously. Then we can compute from that calculation our objective function, which is how many dollars in profit we make. Should have made that with 2 decimal places. There we go. Okay. So I'll mark that cell, fill it in, just so we know that's our objective. And now we come to constraints. Okay. Now, first constraint we'll consider is the budget. Okay. So the budget, Okay, there's a number of ways you can compute this. I'm going to kind of break it down into two different steps. Okay, so the budget says, or the problem says, that we have to spend, I think it's 80 cents. Yeah, 80 cents to make each jar of applesauce, 60 cents to make each bottle of apple juice. So I'm just going to use those two parameters here and some product to multiply. So for every unit we make, we have to pay some cost to produce it. Okay. So I'm just going to label that production cost. Those are all currencies. But then obviously there's also advertising cost. Okay. And each of those is, we'll just literally use whatever values from the decision variables. So it's as if you were multiplying them by a coefficient of 1, and we can sum those up. Now, maybe to do that a little easier, I'll continue using some product to multiply those numbers by just the constant values 1. Okay, so that tells us number of dollars spent in advertising. And then total cost is just the production cost plus the advertising cost. Okay, and that value is the one we want to limit to be $16,000 or less. Oops. Okay. So there's a number of ways you could have done that. I just chose to break it down into two steps. So the constraint isn't on the production cost or advertising cost, it's on the sum of the two. So I just computed them independently, added them together. So adding, still a linear function. So I can still treat this as a linear function of the decision variables. And that's the value I want to constrain. Okay, so that's one constraint. The other constraint is the blending constraint, which says we can make no less than 20% but no more than 60% of our product in applesauce. Okay, so no less than 20, no more than 60. Again, there's a number of ways you can do this. I like to see the algebra, so I'm going to describe the algebra. So if we had our applesauce count of how much we're going to sell, just call that AS, okay? And we divide that by AS plus apple juice, we'll call it AJ, right? So that's the ratio of how much applesauce we make to how much applesauce and apple juice total we make. And we want to limit this thing in two ways. One, we want it to be greater than 20%. And two, we want it to be less than or equal to 60%, right? Okay. So we're going to make that two different constraints, right? One of them is going to be a greater than or equal constraint, and one of them will be a less than or equal constraint. But it's the same value in each case, right? Now, you can look and do the algebraic manipulation. It should come out to something like, I'll use fractions instead of percentages, okay? But 0.8 applesauce minus 0.2 apple juice, okay, is greater than or equal to 0. Okay? So that's just taking the left-hand portion of this that says the ratio of applesauce to total is greater than or equal to 20%. Right? Multiply the denominator over, subtract things across, you should get 0.8 applesauce minus 0.2 apple juice has to be greater than or equal to 0. And similarly, the second constraint you can do, let's say 0.4 applesauce minus 0.6 apple juice, okay, is less than or equal to 0. Okay. If you haven't seen these much before, the pattern, I like to do the algebra and think about it, but the pattern is the thing you want limited, right, will be the coefficient for that thing will be 1 minus the limiting fraction, right? So you want applesauce ratio to be greater than 20%. then 1 minus 20% or 80% times the applesauce minus the 20% times everything else, in this case the only other thing is apple juice, should be greater than or equal to 0. Similarly, if you're wanting to limit it to be less than 60, then 1 minus 60, or 0.4, times applesauce minus 0.6 of the other thing must be less than or equal to 0. Okay? So, we can compute those two things easy enough using some product. So, I will label this greater than or equal to 20%. So, we want 0.8 times applesauce and a negative 0.2 times apple juice. Okay, so those are our coefficients. We're going to multiply those by the numbers, right? Not the advertising dollars, but the actual numbers of product we make and sell. Okay, make that an absolute address. Multiply those by these two coefficients, and in this case, this one has to be greater than or equal to 0. Okay, and to be less than 60% applesauce, right? We want 0.4 times applesauce and a negative 0.6 times apple juice, and we're going to constrain that to be less than or equal to 0. Okay. So, what you can see is that if we spend no dollars advertising, we make a profit of $15,750. We're well under our budget. Okay, so production costs only add up to $6,400. We are technically making more than 20% applesauce because this constraint is not at its boundary or not at the threshold yet. However, we violated the less than or equal to 60% constraint, meaning we're obviously making more than 60% applesauce, right? Makes sense? Okay. All right. Any questions about any of that? So the last thing we would do is tell Analytic Solver platform the decision variables are in cells, in this case B3 and C3. The objective function that we want maximized is in cell D9. The value in D14 is constrained to be less than or equal to the value in F14. Value in D15 must be greater than or equal to value in F15, 0. And D16 must be less than or equal to F16, or 0. Okay? Now, is there an implicit constraint we should consider? I.e., should we prevent spending negative advertising dollars? Okay. There's a few nods. I would agree. Yes, we should. Because the way we've set it up, if you spent negative dollars advertising applesauce, let's say negative $1,000, right? You can effectively reduce the demand, which obviously may make you meet different constraints differently. Also obviously affects your objective, but certainly that doesn't make sense, okay, to negatively advertise your product to reduce the demand on it. So we will use that sort of easy way on the engine tab to say assume non-negative is true, meaning decision variable values must be 0 or positive. Okay? And then we will execute the model. Okay? So it found a solution. In this case, spending advertising dollars on apple juice, right, such that the increased quantity allows for sales to maximize profit. The increased quantity production costs coupled with the advertising costs are exactly equal to our budget, right? and the constraint of making less or greater than 20%, less than 60% applesauce is met in both cases. Okay. Now, are we making the minimum amount of applesauce or the maximum amount of applesauce? In terms of, are we 20% applesauce, 60% applesauce, or somewhere in between? And why? That's not a question on the homework. It's just a question for me. Any thoughts? Less than 20%?
No,
Close to 20%. Okay. And why? Why do you think that?
The applesauce costs more to make, and one of the biggest limiting factors is the $16,000 in cost
Okay.
to produce and advertise.
Okay. Yeah. So you were just looking at these numbers up here and saying that, well, we're making less applesauce. We're probably making close to 20% of total. Okay. Fair enough. So the other way, that's a fair way to answer this. There's not a right or wrong way. What I'm just asking so that you can try to understand the model better. Looking at the two constraint values down here. So the constraint that says you must be greater than 20%, obviously we're greater than 20% because we're not at that threshold of 0 in that computed value yet. 800 is definitely greater than or equal to 0. Okay. And likewise, negative 7,600 is certainly less than or equal to 0. If we were making exactly 20% applesauce, then this value here in D15 would be 0. Right? We would be at the constraint boundary, and this constraint would be considered binding. Right? We would be making the least amount we were allowed. Likewise, for the 60%, if that value computed in D16 was 0, we would be making exactly 60% the value that we want to limit it to. We're definitely not at either of those limits. We're somewhere between 20 and 60%. I agree, certainly we're probably near 20 because obviously applesauce 5,000 is much less than apple juice 16,000. But also this 800 is closer to the 0 than negative 7,600. Okay? All indications which say we're making the right amount between 20 and 60%, we're close to, but not equal to 20%. Okay, you could compute this if you wanted to. The only thing I would say is, remember, we were making a linear model, so our constraint functions have to be linear functions. So you couldn't compute, say, if we wanted to compute, we'll just do it out here. The amount of applesauce divided by the amount of applesauce plus apple juice. Okay, so there you go. We were making 24%. We couldn't place a constraint on this equation to say this must be greater than 0.2, less than 0.6, because this equation is not linear. Okay, in terms of these two values are obviously linear in terms of the decision variables. Okay, so because this equation is nonlinear, being based on decision variables, we would have a nonlinear function. Okay, so we couldn't use a nonlinear function like that in our constraints or objective if we wanted to, and still have a linear model. Okay, all right. So there's the answer. Let's go back to the assignment text. So we constructed the profit. So part B, what are the optimal quantities of apple sauce and apple juice? We kind of saw that. It was, I think, 5,000 and 16,000. What's the optimal amount to spend on advertising? 24,000 or 2,400 on apple sauce or apple juice, excuse me. And the profit, I don't remember, but you could read that off the Excel sheet. Describe the quantitative pattern. So obviously we chose to spend as much advertising as we could, all on apple juice. Okay, and when I say as much as we couldn't have spent more in advertising without violating the budget. Right? So we were using all of our budget between the production of the applesauce and apple juice and the advertising of apple juice. Okay, so that would be the sort of description, I would say. Now adjust the model such that the $16,000 budget can be spent completely on advertising, just meaning we don't have to account for production costs anymore. So it doesn't matter how much production costs we have. Obviously, we're going to make more profit than that. let's just limit the budget, or I'm sorry, let's just limit the ad expenses to $16,000 and see how much we would spend, right? So under this new model, what's the new pattern and which constraints are binding and so forth. And then using the new model, so using the model where we're limiting ad expenses only, not production expenses and ad expenses. So using that model and optimization sensitivity, what per unit profit of applesauce does the optimal solution pattern change at? And you can perform the optimization changing at a quarter at a time. So the steps between, the values can be as big as a quarter. Tell me, with that resolution anyway, at what point does the per unit profit of applesauce cause us to make different decisions? Okay. Any questions about assignment 4? Hopefully that answered outstanding questions. Due at midnight tonight, so still have several hours to work on it. Hopefully this has helped. Certainly, if you have additional questions, see me soon before the deadline.